at Thermal Analysis Labs. He has a Bachelor of Science in Chemical Engineering, as well as a Master's of Science in Chemical Engineering from the University of New Brunswick. Has experience with a lot of different material characterization types, and that includes TMA, as we're talking about here today. So without further ado, I am going to stop sharing here and ask my colleague Alex to get started with the presentation for you all. Again, thank you so much for joining today. Hope you enjoy the presentation.
Thanks, Megan. I'm just going to share my screen and then we can get on to the presentation. There we go. So again, my name is Alex. I will be your host today for the webinar. So in this webinar, I'm going to cover what type of thermal analysis can be performed by Rigaku equipment, just a little background, brush up. Then I'm going to really home in on thermomechanical analysis, which is TMA. And then specifically, we're going to look over the tensile attachment, which is good for thin films, as well as other fibers, other small things. And then I'm going to show quick little short videos over the sample preparation and the loading, just some background behind the scenes, as you could say. Then we're going to take a step back and explain what thin films are and kind of how they're used. And lastly, I'm going to go over some results, or you could say applications of the tensile loading attachment for thin films. So Rigaku is mostly known for its X-ray related technology, but they've also been branching out into thermal analysis equipment. Their thermal analysis can be broken down into three main categories, I like to put it, measuring either mass, heat, or dimension. So under mass, we have the TGA, the thermogravimetric analysis. This is really how mass changes when it's exposed to a range of temperatures. It's good for measuring thermal decomposition or even temperature reactions where mass is gained or lost. Then next, under heat, we have differential scanning calorimetry. This is good for recording, the heat associated with different thermal events, melting, glass transition. There's a bunch of them. Then also there's a combination of them called simultaneous thermal analysis, where we combine them both. We look at mass loss and thermal events in one instrument. And then lastly, the TMA, the thermomechanical analysis, is kind of what we're going to be talking about a little bit today. It's the measure of the expansion of materials due to heating. So each type of thermal analysis has its different strengths and weaknesses. And for the TMA specifically, we can look at the glass transition, the sintering, softening, and what most people are interested in is the coefficient of thermal expansion. These can all be reported by TMA. So taking a step back, TMA is a technique in which the sample size is monitored as a function of temperature or even time as well, if you have a specific heating rate. So the results are often described here in a graph, which then we can use to analyze the curves and the lines to see which events are taking place. So here we can see we have a nice gradual constant slope, and then it changes a little bit right here to another constant slope. This happens when the material transitions from its kind of glassy state to its rubbery state. So here we have a glass transition. And then here we can observe a shrinkage. This is known as the diametric softening point. It's kind of when the rod that is kind of pushing on the sample kind of penetrates it a little bit. So although it might not happen in real life, it's what is observed by the machine, and it's been known as the diametric softening point. So quick aside here, there are some accessories that are available for use with this TMA. So the first one is the humidity unit. I like this one because often in science, we don't overly account for humidity. We try and run our tests in dry or inert environments, or we make the assumption that the humidity is negligible. But whenever we go to apply these materials in the real world, they're exposed to humidity. So that's why Rigaku has made this, this humidity accessory, because some units or some samples can absorb moisture or hold it, and it can impact their expansion. There's also the refrigeration unit. There's not much to say about this. It's pretty self-explanatory. It just lowers the minimum attainable temperature range. And there's also a third one, which is the liquid nitrogen cooling unit. However, it's not really the best with the thin film detachment, which is what we'll be discovering today. So the TMA has a variety of attachments that can be used based on the type of material that you need analyzed. So for objects that can support themselves, the compression loading attachment really works best. So here we can see that there's two rods here. We have our detection rod for the sample and as well for the reference. So we have these two rods because the attachment itself will actually expand when it heats up. So we have the reference to kind of, account for that expansion to get more precise results. So as you can see here on this side, we have a picture of it. Kind of hard to see because it's all made of quartz and you can see through it. But we have the reference, which goes on this side. And this is the detection rod to measure how much the reference moves. And again, the reference is made of the same material as the attachment. Then we have the sample over here, which goes on the other side. And that's what we really want to record the expansion of. So we also have the penetration method. Much like the other one, we have two rods here. We have one for a reference, which again is the same material as the attachment. And then here is where we put the sample, and basically we stab at it, and as the temperature rises, it becomes softer and we can record that. So this is kind of one we're all here to see. There's an old saying that goes something like, you can't push a rope, and well, the same applies to a thin film. As you may know, they're quite flimsy, and it makes it difficult to measure their CTE with a method such as compression. So the tensile loading attachment goes the opposite direction and uses tension to measure their expansion. So there's these metal clamps which hold the thin film, and then it's in this detection rod right here, which moves up and applies a constant tensile load. So as the film will expand or contract, the detection rod will move up and down to keep the load constant. So we set the load and it will stay at the same tensile force over the entire time. And when it moves up and down to keep the same tensile force, that's how it measures the expansion. So although the highlight of this attachment is on thin films, it can also measure fibers, wires, and other small thickness objects. So here, just a little quick video of the thin film sample preparation. So you'll notice that there's a bunch of small divots here, and that's just for different size samples. And as you see here right now, he has a little bit of trouble getting the sample in. That's because it's machined to very fine precision, just so that the sample doesn't go in sideways, or that make sure everything really lines up, because that's really important when you're measuring something of this small of a scale. As you can see, the things that have multiple screws in them there, as I can show you, these are the sample mounting brackets, and they're there so that you can tighten them to make sure the sample clamps are in the correct position, again, so that they're aligned. You'll see right now he is tightening the screw, but not all the way, so that way it gives him the time to adjust the brackets behind it to make sure that it's flush and straight. I've done this myself actually, and he's doing a great job. It's a lot smaller than it looks, and it's really hard to get everything like this on the first try. Not everything's tight. He's tightened both the screws that hold the sample. He then takes off the weight, and then he can loosen the brackets that are behind it, and then the sample should come out. And as well, this is how easy it is to load the thin film sample into the actual tensile attachment. So you can see here, he places it on the detection rod, and then the tensile force is applied, and you'll see the rod move up. Then there's a little metal foot there to the left that will go underneath it to secure it in place in case there's any shrinkage. So I've been talking a lot about thin films. So what are they? It's simple, really. It's just a really thin material that has a thickness that's usually on a scale from around microns to nanometers in thickness. They have a couple uses. They're often deposited onto a substrate to enhance the substrate's properties. So examples of this include increasing the electrical conductivity, increasing chemical resistance, or increasing the reactivity of something, as well as things such as increasing or decreasing slipperiness or even scratch resistance. So oftentimes they're deposited on the substrate, but sometimes they're just used on their own for their own properties. Example of this is copper thin film. Copper is very conductive, and when you're trying to make smaller electronics, you need a small amount of it. So they use copper thin films. As well, it could be expensive, so you want to use the least amount as possible. Thin films are often used in corrosion prevention, again, electronics, photovoltaics, solar panels, lenses, whether it be for cameras, telescopes, and just small micromechanical systems, or they can even be used as, for example, filters, membranes, sorbents. They have many uses. So why is their property so important? One interesting with thin films is that their materials properties vary greatly from that of bulk material, and their properties can even change based off the film's thickness or even the manufacturing method. So if it's created, it could be the very same material, but it's kind of created or a different way, and it can also affect the expansion. So knowing the thin film properties are important to determine the application of its use. So, if you want to avoid glass transition, you want to avoid melting, or if you want to avoid the thin film expanding to a certain amount. So if a thin film is used on a substrate, there could be some issues if the CTE, the coefficient of thermal expansion, is quite different than that of the substrates. They really need to be taken into account. So, for instance, stress can be formed when it's cooled if they have such a high difference in CTE. So we can see here that I have a photo here. There's a thin film and its substrate. The thin film wants to expand more whenever it heats up. But however, whenever the thin film is deposited, its expansion is restricted by the substrate. So stress can form within the film. That's bad because it can lead to delamination, so the two could separate, crazing, cracks could form. We could get deformation of the film or substrate. If the substrate itself is thin enough, we can see warpage of it, or even failure. It just could break, it could crack, it could peel off. So even if the application of the thin film is going to be at room temperature, the thin films are often heated or are often deposited or even made at higher temperatures. So when the film cools, that could be a possibility as well. So when you're manufacturing thin films, sometimes you have to get the film to a desired thickness. So you have to arrange the molecules in a very specific way. This can cause stress within the film, but when the film is heated up, the molecules can relax a little bit, and this is when the stress is released. So some people are interested in seeing this stress, and this is what it looks like in a PEEK film, peak. So this film itself was 76 microns, and it had a heating around 5 degrees Celsius per minute. You can see down here, there's a very abrupt expansion. And then over here, we can see that it kind of shrinks a little bit before going back up. We notice here that the slope of expansion is different, which means that somewhere through this point, it underwent a glass transition. But because there are these kind of bumps and contractions due to stress relaxation, it makes it hard to see where it happened. So what we can do is we can run a second cycle with the film. And here, this is the exact same film, just ran again. You can see that it's much smoother here. Using the 2-point method, we can see the exact point of the glass transition. And this makes it a lot easier for the CTE, the thermal or coefficient of thermal expansion. We get this by doing the elongation, the initial length, and the change in temperature. So whenever the graph goes up and down, it's bumpy, it can lead to some weird results. That's why it's nice to have a nice smooth graph. And the CTE is calculated by the software, so we can use any reference point or get it at any temperature point, which is nice because sometimes you want to use room temperature as reference, other times you want just after the glass transition or any other different specific temperatures. Here, I've added the slope of the expansion to the graph here. It's a little bit noisier due to being the derivative, but we can clearly see the baseline. So here we can see that in the glassy state, it expanded at around 0.02% per minute. And then up when it hits its rubbery state, it goes up to around 0.08% per minute. So this is nice when you want to report the glass transition as a temperature range, because we can clearly see here is where its derivative begins to increase and so where it ends. So now we can report the glass transition as this range. Or it's nice if you just want to get the elongation as a rate. So this also has very big application in textiles. As you see here, we have the expansion of various fibers. By looking at this graph, what does this tell us? You see here in black that cotton shrunk up until around 100 degrees Celsius. This is likely due to dehydration. There was water or moisture adsorbed the fiber. We see here silk underwent the smallest release change. You can see it also had a little bit of shrinkage up until 100, and then it kind of went up a little bit, but it's fairly stable. Here we can see that polyester had a huge drop at around 200, but in the meantime, it was a little bit stable. So I like this one a lot just because it can help remind me what fibers can and can't go in the laundry dryer. A little offside application of it. Here, this is an interesting test where the humidity remained constant, the temperature remained constant, but the humidity was used to determine the expansion from the adsorption of moisture. So if we take a look here, we have silk and polyester. It was held at 25 degrees Celsius. We had steps in the relative humidity from 0 all the way up to 80. And as you can see, the polyester, which is an artificial fiber, didn't really absorb much moisture. However, silk, which is a natural fiber, had large jumps. It increased around 1% at 80% relative humidity. So in closing, kind of the who, what, when, where, why type. So thin films are gaining popularity and they can be applied in various industries. However, one issue is that their properties, such as CTE, can differ from that of bulk material and really based off their thickness and manufacturing method. The TMA thin film attachment, it offers an easy solution to measure the elongation over a wide range of temperatures, humidity, and thickness. So I just like to lastly highlight that the thermal analysis lab at C-Therm is equipped with the TMA as well as a thin film attachment. So we're able to do TMA with thin films of thickness from 10 to 250 microns, a length of 10, 15, or 20 millimeters, as well as a temperature range from -70 to 600, and in an atmosphere of either dry air, argon, or nitrogen. Thank you. That's it for me, and I think it's back to Megan now.
Awesome. Thank you very much, Alex. Now I'm just going to wrap things up with a couple outro slides here, and then we will also get to the Q&A. So if you have any questions, please feel free to put your question in the chat box. Our best to get to them all. Okay, so if you're looking for additional resources, either on the TMA, Rigaku instruments, or thermal conductivity, we have quite a few resources on our website. We have webinars on almost every topic. We have a very extensive tech library as well, or if you're looking for something that you can't find, please feel free to put it in the chat and we'll have somebody help you out. We are going to be at a couple upcoming events for the remainder of the year. The Polymer Testing World Expo in Cleveland, Ohio next week, and also the Adhesives and Bonding Expo Europe, which is in Germany on December 5th to 7th. So please feel free to come see us if you're in either of those areas. And we have another webinar this month. It will be focused on solving formulation challenges of thermally conductive materials in e-mobility. That will be on Thursday, November 30th. So please feel free to sign up if that's something that is in your wheelhouse. And we are also on LinkedIn. That's a great place to follow us if you'd like to keep up to date on new webinars that are coming out or new blog posts or events that we're going to be at. We announce everything over LinkedIn, so that would be a great place to follow us to keep up to date on everything. Now, if what you saw here today was interesting, as Alex mentioned, we do offer the testing through thermal analysis labs on the TMA as well as the other instruments. If you're interested in learning more to potentially have this capability in your lab, that's also something that we can help out with. So please feel free to just write that in the chat and we'll have somebody reach out to you and help you out with that, as well as if you need a quote. And finally, we are going to move on to questions. I saw a few come in as we were presenting there. So yeah, with that, I think we're going to wrap up the live portion of this webinar. Thank you so much to everyone for watching. Really appreciate it. You will receive a recording of this as well if you would like to review or share with some of your colleagues. So yeah, thank you very much, everyone. If you're jumping off here, have a great day, and please stay online if you'd like to be part of the Q&A. Thanks.